You're having issues with your performance? 200 units and not enough frames per second? Let's fix this! So on this video we're going to talk about an optimization technique which is all about a way to optimize your game a little further by reducing the physics process frame rates. But the issue with that is that your game is going to break all over the place. So whenever you use physics process functions, those are going to be called a lot less, which results in lagged movements, camera movements lagging behind, and whatever you set up with using the physics process is going to basically break. If you're looking for another way to optimize your game in which you have performance issues, this is another one. Depending on how you're going to run physics on your project, this can break or make it work. So the way that this works is you interpolate the unit graphics with the position of the object through a animation. In this case, I'm using a basic tween with linear interpolation. My project is not depending on the physics calculations. We are using physics to move units. We're not using physics to calculate ragdolls or anything else. So if your game is running with physics, this solution may not work all that well, because basically what we're going to do is to change the physics frame rates, which means you're going to see it's lagging behind if you need to see your physics objects. Okay, so this is what I have with the project that is not running that optimization. We can see that we have around 70-75 FPS, but once all units start to move, we're going to get it low as 30 FPS 40. So most of the frame loss is due to costly physics operations. Each unit is moving a physics box, and we have the navigation as well, which calculates a bunch of different things. So in short, 30 FPS. And we also have to remember that we are using a viewport for the fog of war, so a bunch of things are starting to add up. So we can see that moving all the 200 units will get around 30 FPS depending on the pathway. Not all that great. So we have to make it better. So this is the project that is using the optimization, so let's just run it. And as you can see now we stay around 60 FPS. So we don't know how much units we're going to have on the game on the final product, but you can see that we have gained a lot of FPS. So the trick that I'm doing here for the optimization is actually a pretty simple one. It's basically hidden under the project settings. You can see that if you come here to the physics tab, remember that your advanced settings must be turned on so you can see everything. To reach here on common, you can see that we have some things here. So one of the things that I changed was the physics ticks per second. Normally is around 60. What I did is set it up to 10, and I also reduced the maximum physics steps per frame from 8 to 2. What exactly does happen by changing this? So if you ever used physics functions on your game, they also will be affected. So you can see that here for the description of this on the editor, it says that is the number of fixed iterations per second, which means how often the physics simulation runs. So this means we are running 10 physics ticks per second, and each tick can have up to 2 steps per frame. So this means how many physics ticks are going to happen per second, and this is basically going to calculate the maximum number of physics steps by each frame. This is to avoid having a lot of various expensive physics simulations trigger even more expensive simulations. So this is to somehow limit how many physics simulations are being calculated. So you can see here that the default is 8 and we apply it to 2. So just by changing these two things, you're going to get a lot of changes. So let me go back to the other project, which was this one, and let's change that and see the effect it has. Physics, common, and we change it to 10 and 2. So just by changing that, let's run our scene and see how it applies. You're going to see a lot of things break on your project. Of course, you're going to gain FPS, but as you can see, first issue, our camera movement is lagging a lot. Second issue is, as you have guessed, our navigation is pretty much lagging as well. So what exactly is happening here? This is exactly what we want. We delay the physics calculations so we can have a lot less precise calculations. So this is exactly why it's running at a higher FPS. But we have to do some changes if we want to use this approach. You have to change how you use the physics calculations with your functions and with your project. And this also means a lot less accurate collisions. So let's say that your project is a first person or a third person. You will not want to apply this type of optimization because this is going to mess with your physics. It's going to make them a lot less unpredictable and less precise. What you want to apply this is, like in our case, we are making an RTS and we don't need all that physics precision, so we can get away with just a little bit. So that is why you can benefit from limiting your physics frame. Now, limiting your physics frame rate have the issues you are seeing here. So we are going to take some steps here to turn this. So here is the project that is running those optimization, but is also running some changes. And as you can see, it's not noticeable. So yes, if you switch pretty fast, you can see that it's not in real time, it's not all that. It does not have the rapid response, but I think the trade-off here for the frame rate is a lot more important. So let's see the steps you should take if you reduce the physics frame rate for your project. Let's address first why the camera movement was impacted, and we're going to see the importance of changing the physics frame rate. So let me go here to my scripts, and I'm going to find the script for my camera. I believe it's RTS camera. So right off the bat, we can see here on our physics process. Oh, what is exactly happening when you change that? Well, the thing is, when you change the physics frame rate, this function here for all your nodes, scripts, whatever runs physics in your project is going to be affected. So when you are reducing from 60 FPS to 10 FPS, this function is going to be called 6 times less, which means that sloppy lagging you saw with the camera moving. So this means that if you want to still have functions running on a nice frame rate, like you have smooth camera movements and stuff, you're going to need to change your functions from the physics process to just process. So why I didn't do that on the first place? Well, when you are using the physics process, you know that you are sticking to 60 FPS. So if your project is not going to change the physics process frame rate, you can benefit with some performance gains by using the physics process instead of just process. Because if you're not using vsync and you're using process functions and your frame rate is higher than 60, you're going to have a lot more performance cost to running those functions. Of course, the benefit of having process here is that our functions are going to run a lot smoother because it's going to run a lot more. So now if we run our scene with just this basic change, the functions that calculate the camera movements, zoom, rotations, etc. now are going to be updated by a process and not by the physics process. So now we should be able to see no delays whatsoever on the camera movement. So as you can see, just by changing the frame rate for your entire project on the physics side of things, you can break a lot of things. So depending on your project, expect some bugs if you are trying to change the frame rate. So we fixed the issue with the camera movement, and possibly you can update a lot of your code that uses physics process functions to just use process. But now, as you can see, if I try to move my units, I still have that lag, because the units are still calculating using the physics process. And not only that, but if you remember, we already implemented a bit of optimization. So yeah, this is the one. So it's the unit prefab. So I'm going to be updating you guys on why it's called prefab. So this is for future stuff. So here's the code for my unit, and I believe it's on unit base. So my unit prefab is extending the unit base. I'm going to talk about this on a future video whenever I finish that. So going back here, let's see what is happening on the physics process. So as you can see, we already implemented an optimization. But when you do this, you're saying that whenever your physics frame of the engine divided by 2 are equal to 0, then you can run this code. So this basically means to run this code by each 2 seconds of that physics frame. However, this physics process frame is already being called less than 6 times, so from 60 FPS it's reduced to 10 FPS, which means that this function is actually calling at 5 FPS. So if we can now remove basically all of these optimization because we don't need it. So now this function is already optimized, whereas before it was running at 30 FPS, now it's going to run at 10 FPS. So let's continue here, and this is the one that calculates our movements. So we can also comment that. So we have increased the physics rates of these functions. So now if we run their scene, we should see a little bit of improvements. But there's still going to be an issue with the movement. Going back here to our scene, and if we move our units, we're going to see that they still have a little lag. While some of the behavior have been improved, we can see that a lot is being still lagging behind. And as you can see, even the speed of the units have increased because we reduced the physics frame rate, because the function is using delta in a lot of calculations. Delta has increased because of the low frame rate. Now a lot of the function have increased the speed of the units. So we also need to reduce that. So you can see that it's going to impact almost anything in your project that uses physics calculations. So be very wary of that and make sure that you test everything before you're doing this. Okay, so what we should do to fix this? Well, you can switch this back to process, but if you do this, we are going to lose the performance we have gained by decreasing the frame rate. And now it's going to run even slower than before, because now it's going to run faster than 6 FPS. So this is not a solution. You can see that we have here an issue with calling functions with super, so let me fix that because I did not have a process function on the other script. So if we run our scene, we'll see that performance has decreased. So we do not have any gains whatsoever. It's still around 30 FPS. So yes, the performance has increased around by 10-15, but we still would like to increase it a little more. Because what is happening now is that this function is being called by this FPS. So we are running functions around 40 and 50 FPS. But there's still some stuff that is inside Godot that is actually being reduced. A lot of the physics calculations are still being run by 10 FPS despite this one. So let's fix this. So one of the things I'm going to fix is by changing my unit speed. So from 8 I'm going to reduce it to 4, and I think that's going to look alright. And let's turn this back to physics function. So we want this to be a physics. And also let me update my extendable function here. Let's save it. So how we're going to fix this? We need to separate the unit graphics from the unit itself. So if we go here to our unit, what we should do is first select our unit graphics, which holds everything we can actually see in the game, to be top level. So what this actually means? Top level means that transformations are not going to be inherited from its parents, which means that this node no longer respects its parent. So whenever this parent moves, the unit graphics are going to stay in place, which is something we actually want. So we want to update the unit graphics by code instead of the updating by transform. So this is the actual unit itself, which calculates physics and the navigation. So this can lag behind, and we can simply through code interpolate a function to move with that. So the movement is going to follow this parent object, but interpolate it through an animation. So let's see how we can do that. So in the unit code, let's go through the part where it calculates navigation. So we are going to still use physics process. So the first thing we need is to create a function that is going to interpolate. So let's create a function that is going to interpolate the unit graphics. So we can see here that we have an interpolate function. So this function is going to basically ask for a new position to move the unit's graphics. So this is pretty simple. We're going to use this with a twin function to make the interpolation. Let's say that after we have calculated everything, we're going to do the interpolation itself. So by each physics process, what we need to do is to first create a twin. So let's do a create twin. So if you don't know, by doing a create twin, which is a function inside Node, you generate a twin which has a lot of nice stuff to do animations with interpolations and stuff. So let's focus here on our unit. So we have created a twin, so this is already a twin, and we can access it by putting a dot here, and we can do a set transition. So trans here is going to represent which type of transition we want. So a tween is going to do something with an initial value and an ending value with a transition type. So it's going to do basically an animation. So here what we want is to do a tween.transLinear. This means that our transitions are going to be linear, so we do not want the animations to be smooth from the start and at the end being fast or whatsoever. We want a constant speed throughout the positions of the unit. So you're going to need a transition linear. And we also want to use a tween method. So this is the part where we're going to use our tween here. We are going to basically call our interpolate function for each physics process frame, which is running on the physics process function. Then we're going to generate a new tween. We're going to set its transition to be linear, and we're going to use that tween with a method. So you can basically think this as setting the tween here. So we are actually running two functions on the tween itself. So we want to use the tween method. So the first argument here is going to be which is the method that you are using. The second method is which is the starting position. So which is the starting value. The starting value is our unit graphics position. Then it's going to ask from that starting position, where do you want to go? So the place where we want to go is basically our global position. So as you can see, now we are starting on the unit's current graphics position and ending at the global position of this unit. And lastly, we can give a duration to this function. So here, depending on the project and our physics frame rate, you can change this to your needs. I found that 0.25 seconds works alright for my case, so I'm going to leave it at that. Now we are moving our unit graphics to that position and alright. And as you can see here, there's an issue because the y-coordinate is still being captured. And the y-coordinate should be on the raycast we did so the unit stays on the ground. So we are raycasting a ray from the top of the units to the terrain so we can find the height position to place the units so they are always on the ground, the graphics at least. So what we want here is to create a new variable which is going to be our new position, and it's going to be a vector 3, which is going to be always equal to our global position. However, when we check here the raycast, we're going to say that instead of your unit graphics, we're going to say that our new position dot y coordinate is going to be equal to the raycast result position. And now we can simply use this new position here instead of the global position. So we are still using global position, but the y coordinate is being changed to the raycast we are doing here. Now we can run the scene and we can see that the changes that this code has done. So now we have our units here, and if you select all of them and try to move, now you no longer should see that issue where the units itself. So as you can see, the units now no longer lags behind their position. They are being interpolated using a tween, which helps with performance. So now our performance is around 60, whereas previously was around 30. And that was basically setting the frame rate. So now we have another issue. If you see, all of our units are not setting the rotations. And as you have guessed, that is because we changed it on our units here. We changed it to be top level. So it's not going to respect the transformation for its parents, which includes rotation. So if you were to set our code here on the base and we go to the physics process, it's going to be a place where we calculate our rotations itself. Now, this rotation is calculating, you guessed it, the rotation of the object itself. So it's calculating the rotation of the units. Whereas now we want the graphics to be updated. So now instead of the unit rotation itself, we're going to set the unit graphics node 3D to be rotated. This is going to fix that issue we had with the units not rotating. So now if we run our scene, we should no longer have that issue. So now if we run our scene and remove our units, now they should rotate adequately. So now we have gained a little bit of performance at the cost of less physics process frame. So yay, that works. So yeah, just by changing your physics process rate and using an interpolation with the tween example that I did, there are other interpolation methods you could use, but the tween is more simple to use, so I chose that instead. You can see how this is working. And you want to see something nice. If you go here on the debug and say visible collision shapes, So now we should be able to see the collision shape of the objects. You're going to see that the collision shapes for the units are still lagging behind. So we are going to see our optimization in real time here. So if we select our units and try to move them, you're going to see that they still are lagging behind. But the beauty is that using the interpolation method, you still see them moving as they did not. So that is one of the reasons you do not want this for a game where the physics needs to be more accurate. You can see how this is going to become a problem. And you can see also why our project was having physics limitations. Running 200 units moving on a terrain is not all that simple. You can see we have a lot of calculations. And this big sphere is being used for the fog of war. So this is an array 3D. So a lot of this now should allow you to have a little bit optimization. So now we have one extra bug to finish here. And as you can see, whoa, units are not respecting the Y coordinates. So let's see why that is the case. And of course, is because I forgot to set it up here. So yeah, the issue is that on my interpolation, I deactivated the Y coordinates. So I did this because I was experimenting with something on my project. So the interpolation function should have the interpolation of the units. So you can safely do unit graphics position. It's going to be equal our new position, so we don't have to worry about each one. That was an experiment I was doing. So that was why our Y coordinates were not working. So now they should work. So yeah, that fixed the issue. So my bad, I did not notice it. So as you can see now, the player does not even know that the game is running 6 times less physics calculations. So if you ever wanted to know another way to optimize your game and you have a lot of things happening behind the scenes and you don't know what to optimize, you can reduce the physics frame rate. But be mindful of the impact it's going to have throughout the code on your project. So all of the functions that your project runs physics process, you're going to want to keep an eye out for those issues.